So you're going to be really into this, which is perfect because this is a good lecture. This is like going to be a little bit difficult lecture. So the plan is to use the next hour to talk about the sum check protocol. And then I'll talk about the applications of the sum check protocol to illustrating some of the power of IP, this class IP that I introduced in the first lecture on languages having interactive proofs. And then I will talk about the GKR protocol, the protocol by Goldwasser, Kalai, and Rothblum. And then if there's time, this is a sort of a not really very technical part. I have about 10 minutes at the end. Maybe we'll go over 10 minutes, we'll see. Just setting the stage for SNARKs and what I think will come later in the week. So before we get to that, actually, this is the first lecture, I think, where we get to use some of that algebra that I talked about earlier this morning, and where we get to see some of the applications of algebra to complexity theory. So just to kind of like set the stage, I guess, I mean, you remember algebra, I think you've all taken algebra, but by show of hands, how many people are already comfortable with Galois theory? Oh, wow, that's great. So you can explain it to me later, actually, because I don't really know it very well. I tried learning it several times, but yeah, but we don't need anything quite that complicated. If you know some basic, you know, you don't even need a group, you need a field, really. If you know what a field is, you're probably fine. And we have this very important fact that you have probably seen if you've taken an undergraduate algebra class, which is that if we let F be any field and take a non-zero polynomial P of degree at most D in that field, then this polynomial has at most D roots. Okay, you're all familiar with that. You're all comfortable. You've probably even seen it before algebra, but not with the field, maybe with the reals or the complexes. And we're going to get a lot of mileage out of something, you know, as simple as this and a small extension of it. The extension of it that you may not have seen, but it's not very difficult to prove, is that the same kind of a thing holds if you consider multivariate polynomials. So if we consider a polynomial in n variables over a field, a non-zero polynomial, where the total degree is at most d, the total degree being defined, or the degree of a term being defined as the sum of the degrees of the variables in that term, and the total degree being the total degree of a polynomial being the maximum of the total degrees of its terms. Then the polynomial has at most d times f to the n minus 1 roots. And I've given the 1-line or 2-line proof here. I won't go through it. You can look at it at your leisure. And you know, it doesn't maybe look like it's going to be as useful as in the first case, because in particular, if our field is large, then we went from a situation where if we have a very low degree polynomial, we went from having a relatively small number of roots to the case where we can now have, okay, it's bounded, but this can be quite large if n is large and if the field is large. But nevertheless, this is actually very useful, because when we apply these two theorems using something called the Schwarz-Zippel lemma, it's going to give us the same quantitative sort of result. And what this lemma says is that, and this is just a corollary really of what I had on the slide previously, is that if we take a multivariate non-zero polynomial over a field with bounded total degree, so total degree d, and then if you now pick a random assignment to all the variables and evaluate the polynomial on that random assignment, the probability that that will evaluate to 0 is at most d over f. And this is just a counting argument or a simple probabilistic calculation, right? You just divide the number of zeros by the total number of assignments, and you get that as your answer. Okay? And this too is something that's extremely simple, right? And yet has hugely powerful consequences, as we'll see in this lecture. Another corollary, which is almost really just a restatement of this Schwarz-Zippel lemma, is that if we take two non-equal polynomials and look at the probability that they agree, if we evaluate them each at the same random point, then that probability is also bounded by d over f, simply because their difference, if they're non-equal, then their difference is a non-zero polynomial of total degree at most d. Okay, so everybody kind of comfortable with what we have so far? Now let's talk about the sum check protocol. So those mathematical preliminaries are enough to give us something, like I said, very powerful. So the basic overview of what the sum check protocol is doing is the following. And for the moment, like when I talk about the sum check protocol, it's going to look kind of abstract. It's going to be an interactive protocol, but maybe you might wonder why anybody would care about doing something like this. But then when I show the applications, you'll see exactly why one might care about these kind of problems. So the setting of the sum check protocol is that we have a prover and a verifier, right? As in the case of interactive proofs we've been talking about a lot already. And they have a common input, a multivariate polynomial P. And the prover wants to convince the verifier that if you take the sum of the evaluation of that polynomial at all points in the Boolean hypercube, then you get some particular value. This is just a field element. You get a particular value H0. Okay, so all we're doing here is we're evaluating this polynomial P at 2 to the n points, where those 2 to the n points correspond to all ways of assigning values to the variables that are 0, 1. Okay, note that 0, 1 are in any field, so this makes sense regardless of the field we're working over. And this is well defined, and the sum, of course, is well defined over any field. So this statement makes sense. And the thing to note here, right, is that the verifier could compute this on its own, right? There's nothing hidden at the moment, right? Everything is public. The verifier can compute this on its own, but it would take time 2 to the n, or at least 2 to the n, because it has to do 2 to the n evaluations of the polynomial, unless it had some, unless the polynomial had some structure or something. But there are 2 to the n points at which you have to evaluate this polynomial. And so it would take time 2 to the n. And depending on n, either that's infeasible or it's just a long time, and the verifier might like to be able to do it faster. For now, it's just you can just think about n as being large enough that doing 2 to the n computation is infeasible for the verifier, and the verifier just wants some way to be able to check that this claimed sum is indeed the correct value without doing 2 to the n work. And actually, it wants to do it using polynomial work. Okay, so we want a polynomial time verifier here. For now, we're not going to care about the complexity of the prover. Actually, you can see that if the prover, for the prover to come up with this value H0, not to mention prove anything about it, the prover also has to work in time 2 to the n. So we're not, at this point, worried about the prover, and we're not reducing the time of the prover. We're only focusing on the verifier and trying to come up with an interactive protocol that will allow the prover to convince a verifier, while the verifier does a lot less work than it would have to do to check the statement on its own. And this is one of the things I mentioned as a benefit of interactive proofs and interaction in general, is that we could potentially offload some of the work, move some of the work from the verifier to the prover, have the prover do more work, let's say, with the trade-off of having the verifier do less work. And I know people are not shy, so you can raise your hand if you have questions at any point. So here is the entire protocol, actually. So let's go through it slowly, because it's a little bit of a complicated protocol, and we'll analyze it in the next couple of slides. So again, the common input is this value P. Let's assume that the prover already told the verifier what the claimed sum H0 is. And what they're going to do in this protocol is they're basically, or the prover and the verifier are going to interact in a series of n iterations, which will be, depending on how you count rounds, roughly n rounds. And what they're going to do is in each iteration, they're basically going to strip off, or you can think about them, the prover helping the verifier to strip off one of these summations. Let's see how that's going to work. What the prover is going to do, so I'll talk about what it does in iteration 1, and then we can just go through it again and see what it does in a general iteration I. So in iteration 1, what the prover is going to do, it's going to send the polynomial that corresponds to everything after the first summation. Okay, it's going to just take away the first summation. If you take away the first summation, right, you're summing out over variables x2 through xn. And so what you're left with is only a single free variable, namely x1. So that's going to be a univariate polynomial. And the prover is going to send that univariate polynomial to the verifier. The verifier is then going to check that the degree of that polynomial is at most what it should be. Okay, what do I mean by that? Well, what I mean by that is that the polynomial P on the inside here, right, there's some degree of x1. That degree is not going to change as you sum over the other variables, x2 through xn. And so the polynomial that you get by evaluating the summation up to the second to last summation is going to be of at most that degree in x1. I mean, maybe there are cancellations, maybe it's lower, but it can be at most the degree of x1 in the original polynomial P. So if the degree is higher than that, then the verifier knows the prover was cheating. And then the other thing the verifier is going to do, it's going to check the final summation on its own. So it's going to take the polynomial P1 of x1 that it got from the prover. It's going to evaluate that polynomial at 0 and at 1 and add those two together and check whether that's indeed equal to H0 or not. It's just the verifier is doing the outermost summation on its own. So great. Now, how do we know that that polynomial that the prover sent is actually the correct polynomial? The prover could have sent anything. Well, what we're going to do is we're going to have the verifier choose a random evaluation point for that polynomial. So in the first iteration, it'll choose an evaluation point R1 uniformly from the field. It'll evaluate the polynomial at that value to get some field element, right, H1. And then it just sends that value to the prover so the prover knows, what to do next, essentially. Okay, so after that first iteration, what have the prover and verifier done? Well, the prover and verifier have now together, right, stripped off the outermost summation, and they've reduced this claim about the sum over all n variables being H0. They've reduced that to a claim about a summation over n minus 1 variables being equal to a new value H1. Okay, where that value, I guess I don't quite have it on the slide, but it's going to be given by this innermost expression here, where now we're in the second iteration. R1 is fixed to some particular value, and x2 through xn are the remaining indeterminates. Okay, so in general, then, just going over what happens in the ith iteration, in the ith iteration, we essentially have a claim that the summation over, I guess it's n minus I plus 1 variables, with the initial I minus 1 variables being fixed, we have a claim that the summation of that is equal to some particular value hi. The prover helps the verifier strip off the outermost summation, and then they reduce that to a claim about the summation over one fewer number of variables and some new sum hi plus 1. Okay. We're going to go over in the next slide why this is sound, and it may make a little more sense if you didn't catch everything, but that's the basic idea.
The third step, what is happening there?
So in the third step, so in the third step, what's happening is the following. So, and again, let's focus on the first iteration. So in the first iteration, the prover sends a value to the verifier, sends a polynomial to the verifier, and it says, okay, this polynomial corresponds to the summation over x2 through xn of this polynomial. Prover might be cheating, okay? Let's say the prover were cheating and sent the wrong polynomial. How could we catch it? Well, what we're going to do is we're going to evaluate what it sent at a random point. And so the basic argument, and we'll formalize this in the coming slides, is that if the prover sent the wrong polynomial, then when we evaluate at a random point with high probability, it won't be equal to the evaluation of the correct polynomial at that point. This was the correlator we had a slide ago. And so if it's not equal, which will happen with all but negligible probability, then the claim going into the next iteration will be wrong. And so that's going to propagate down the iterations till the end. Yeah.
Just to clarify, I think, right?
And by the way, I didn't get to finish this last step, so I'll get up to that in a minute. But yeah, go ahead.
The transcript is just the challenges are, and this H's, and each H is just in field.
The H's actually are being computed by the verifier. So the only if you want to minimize communication, what you have is P sending a polynomial in every round, a univariate polynomial, and V sending back a random field element.
Sending a polynomial means sending all the coefficients of the polynomial?
So you don't have to do that, and you probably don't want to do that. You can, it doesn't really matter as long as you send something that the verifier can evaluate. What you might do in practice is, if it's a degree D polynomial, just give the evaluation of that polynomial at D points, and that will specify, or D plus 1 points, and that will specify the polynomial. I want to say it almost doesn't matter. I mean, in practice, if D is large, it might matter, but a lot of the applications have D small, and then it doesn't really matter that much. But you can specify the polynomial any way you want, as long as P and V agree on how you're going to specify it. So let me just say quickly what just the final step here, right? So you do this iterative process down to the end, and what happens at the end? You have no more variables to sum over, but now you've assigned all the indeterminates to some concrete but random values R1 through Rn. And at that point, the verifier also has some claim that the polynomial evaluated at R1 through Rn should equal some value Hn. But this is something the verifier can check on its own, right? The verifier has the polynomial, it shows the random points R1 through Rn, it can just do the evaluation and check whether it's equal to Hn or not. And if it's not, it rejects the entire proof. So this is what I was saying before, let's actually, think about it before we go on to the next slide. So what's the overall structure of the argument? The overall structure is that, let's say the prover is lying and H0 is not the correct sum. Well, I'm almost saying what's on the next slide, but it's okay. So if the sum is not equal to H0, then when the prover sends the polynomial P1, which is everything up to the last summation, then either this check here is going to fail, right? Or the prover has to send a different polynomial. If the prover sends a different polynomial, then with overwhelming probability, the verifier will pick a point at which the polynomial that the prover sent does not match the actual summation of the innermost n-1 terms. And then they proceed to the next iteration. And then each iteration, if the sum is not correct, with high probability, the sum is still going to be incorrect at the end of the iteration. Keep going to the last iteration. And then the last iteration, the verifier just checks it on its own whether this is true. And still with high probability, this will fail if the original H0 was incorrect.
Basically, like this, splitting and some check protocol of one smaller dimension.
That's exactly, it's a recursive protocol. I mean, you can actually, if you could program it recursively if you wanted to, and say, okay, we have, and that's how the proof is going to go actually. So we're going to say, okay, let's assume we have a sum check protocol for univariate polynomials. Can we build it up into one for bivariate polynomials? Okay, now let's build it up to trivariate polynomials, etc. So completeness is clear in the sense that if the prover is not lying, and that's indeed the correct sum, and if the prover does what it's supposed to do in every iteration, then the verifier will always accept. That's just by the structure of the protocol. By the way, I'm just want to calibrate and make sure, right? Everyone's kind of clear. So like when I have this going on in iteration I, so what do I have here? I've fixed the value of the variables 1 through I minus 1. I'm summing over variables xi plus 1 through xn, and therefore the only free variable remaining is x1, xi rather, and so it's a univariate polynomial in xi. Right. Sometimes it's hard to keep track of what's a field element, what's a polynomial, etc. But
I kind of see how this maps to your example earlier with the Hamiltonian cycle, where you're always just revealing one aspect of the solution.
well, except that here we're not claiming and not intending to get any zero knowledge. There's nothing hidden here. It's a soundness thing rather than a zero knowledge thing. So it's
hidden from the verifier in the sense that the verifier is assumed to not have the same computational ability.
well, it's also the fact that sorry, what'd you say?
It's hidden from the verifier only in the sense that the verifier is assumed to not have the same computational strength.
Well, that is true, but well, okay, that is true. That's one way to look at it. I was thinking about it a little bit differently. It's similar to the Hamiltonicity protocol in the sense that the verifier is making a random selection that the prover doesn't know in advance. So even if the prover were and this works against an all-powerful prover, even if the prover were all-powerful, it doesn't matter because the prover doesn't know what random point the verifier will choose to evaluate it at. And in the Hamiltonician protocol, the prover didn't know what challenge the verifier was going to send. So let's look at proving soundness, right? So the theorem we want to prove is not only soundness, we want to actually give a concrete bound on the soundness. So let's imagine that we have a polynomial p, which is an n-variate polynomial of degree di in each variable. So here I'm no longer looking at the total degree, I'm looking at the degree on a variable by variable basis. And my claim is that the sum check protocol has soundness error bounded by the sum of the di divided by the size of the field. Meaning that if the prover claims an incorrect value h0 for the initial sum, then it can succeed in convincing the verifier in running the sum check protocol with at most that probability. So of course, the larger we set f, the lower the soundness probability is going to be. And if we want this to be cryptographically sound, we're going to want the size of the field to be at least 2 to the lambda times the sum of the degrees. But that's okay. That just means that the representation of field elements is at least lambda bits, but no problem working with fields of that size. So the proof is going to be by induction on n. We'll look at the base case and then look at the inductive argument. So the base case is when n equals 1, and we're arguing about univariate polynomials. And again, the protocol is well defined even for univariate polynomials, even though the verifier can certainly compute this by itself with no trouble. So what does it mean in the univariate case? It means that the prover is making some claim about the sum of a univariate polynomial over 0, 1. And let's imagine that that claim is incorrect, right? The H0 is not the correct sum. And we want to see what the probability is with which the prover can cheat. That is not supposed to happen. Okay, we need technical support. Okay. I hope I didn't build some graphic that's gonna, I don't even have.
Do any
it
of the
yet.
later slides work, or it's just?
It
like
doesn't
a
seem to
slide?
be working. Let's see if I use the keyboard. Yeah, I don't know what's going on. That's weird.
Which vertical machine?
We can try. Yeah. And I can do it from my laptop. So as you can see, it's obviously correct.
I think it's the problem of the slide to
If I can try to resend them or I can.
let's
Slides.
sit down and open it again and see
Okay.
if it works. Do you remember which page you're at?
Yeah, right there, it's fine.
Oh, it's possible.
There we go.
Okay.
It's just Adobe acting up.
Okay, maybe it's too large of a file. Okay, thank you. Okay, so, right. I hope this proof is clearer. So yeah, the prover sends an H0 and it's an incorrect claim. So now there are two possibilities, right? Remember what the protocol says. The protocol says the prover should send the verifier a polynomial P1, which is supposed to be the sum over everything other than the outermost summation of what's inside. In this case, it's just going to be, it's supposed to send just P itself, right? But the prover may lie, right? So the prover sends some value P1, some polynomial P1, and there are two choices, right? If P1 is equal to P, then the verifier catches the prover right away, right? Because if the prover sends P1 equals to P, well then P1 evaluated at 0, I mean, this is just doing the summation here. Well, it's not equal to H0 because it's the wrong value. And so the verifier is just immediately going to reject. So, okay, what's the prover's best option? Well, the prover's best option is to send P1 not equal to P, satisfying this equality, and hope that the verifier will nevertheless accept. Well, let's see. If P1 is not equal to P, then what does the verifier do after this check? What it does is it picks a random point and evaluates P at that random point and P1 at that random point and checks whether they're equal or not. So if P1 is not equal to P, well, what did our corollary say, 3 slides ago or so? It said that V is going to accept, right? These are different polynomials now. What's the probability that they agree at a random evaluation point R1? It's exactly D1 over F, where D1 is the degree of X1 in this polynomial. Now it's just induction. So let's imagine that we prove the theorem up to n minus 1 variate polynomials. We want to now extend it to an n variate polynomial. So again, let's say we have an n variate polynomial and we're looking at the sum over the hypercube, and the prover claims that that sum is equal to some value H0, which is incorrect. So let's define, So let's define P1 star to be the innermost summation, right? That's what the prover was supposed to send. It's again a univariate polynomial just in the variable X1. So now again, the prover has two choices, right? If the prover sends P1 equal to P1 star, then it gets caught straight away by the verifier, because the verifier is just going to apply the outermost sum, find that it's not equal to H0 and reject. On the other hand, if P1 is not equal to P1 star, then the probability that they're equal at a random evaluation point is going to be 1 minus D1 over F. So basically the probability that they agree is small. It's D1 over F. And in that case, right, assuming that they're not equal, then the value H1, which is exactly equal to P1 evaluated at the random point, is not equal to P1 star evaluated at that random point. What is P1 star evaluated at R1? It's exactly this expression on the right. So what that means is that with probability, what do I want to say? With probability at most D1 over F, well, let me say it differently. This is why I wrote it this way. With overwhelming probability, right, except with probability D1 over F, this is going to be the case. H1 is not going to be equal to the summation of what's left. And we can now apply the induction hypothesis to the sum check protocol over polynomials of degree n minus 1, right? Because what we have inside here now is we fixed one of the variables to some fixed value R1. And this is really, what's inside here is really now an n minus 1 variate polynomial that we're taking the sum over the hypercube. Okay. So that's actually, about it for the analysis. So you can see it's very short once you have the protocol itself. The proof of soundness is actually very clean. Any questions on the protocol or on the soundness proof?
One smart on why exactly are we estimating the probability of the P1 equal to P1 star on that point?
Yeah.
It seems to be what we want to guess is that P1 of 0 and P1 of 1 are equal to the previous value, not that they're.
No, so you have to think a little bit about what's going on in the ith iteration, right? So let's think what's going on, or maybe not the ith iteration. Oh, this is all looking at the first iteration. So in the first iteration, right, what's going on is that the prover is sending a polynomial, P1, and that polynomial is supposed to be the sum over everything but x1. But the prover can send whatever it wants, obviously, so we're going to have to check for that. Now, if the prover sends the correct polynomial, then it's clearly going to be caught, because what's the first thing the verifier does, other than checking the degrees? The first thing the verifier does is do the outer summation itself and check that that's equal to the claimed sum, H0. So if the prover sends the correct polynomial, it's caught straight away, and that's it. If the prover sends an incorrect polynomial, okay, whatever that polynomial is, then what the verifier does next is it picks a random point, and it evaluates the polynomial that the prover sent at that random point, and interprets that as a claim about a summation over one fewer variables. So it interprets that as a claim, as this summation, actually. It can't evaluate this thing yet, but it interprets it as a claim that, so what does it do exactly? The verifier takes the polynomial P1 that it received, evaluates it at R, and then goes to the next iteration. So evaluating it at R1 just gives you H1. So that gets carried over to the next iteration. And then what else gets carried over to the next iteration is that now we're summing over everything except x1. And the polynomial we're summing over has the first variable fixed to R1. And that was exactly what we defined P1 star as. So the fact that these are not equal means that these are not equal.
Exactly, this is the point, right? Like if they would agree on this random point, then it wouldn't.
Then you lose.
One would actually be equal to the sum of all.
Yeah, and then the prover wins. And then the prover wins, but that only happens with bounded probability. So that's the point. So the prover can cheat the verifier, but it only happens with bounded probability.
That will only be found out at the end, or already in this step?
It'll only be found out at the end. Yeah, I mean, it depends a little bit what the prover does, but assuming the prover doesn't do something stupid and make this check fail right away, then what would what will we find out at the end? If the prover wins or if the prover loses? Or I don't know which. I guess both.
Yeah, I don't know.
If the prover, let's see. Well, if the prover happens to succeed, and
If it was cheating and this.
yeah, so if it was cheating and it gets, I mean, let's imagine actually the field could be small, right? The field might only be, twice the size of D1, in which case you only have probability half of catching the prover, and then it can succeed with probability half maybe. And it only has to succeed once. It's not like the sequential repetition where you have to succeed every time. Here, if the prover succeeds once, it could just win till the end. Once it wins, all the summations are correct, and then it continues to win till the end. So in fact, if you set parameters that way, then the prover could succeed with pretty high probability, higher than half. But let's assume not. Let's assume F is really, really large. Then this event that the polynomials are equal basically doesn't happen. And then you go down to the end, and the final check fails, and the verifier.
Only be the very final.
Yeah, right. Only at the end the verifier would catch the prover for sure.
I guess the final soundness error now we just get by the union bound of like.
Well, yeah. So I mean, the way I structured this proof, right? The induction hypothesis was that this protocol that they run has soundness bounded by D2 plus Dn, D2 up to Dn divided by F, and then you take a union bound with this and you get the claimed result.
Even for a small field, right, you could amplify the soundness by just running it several times.
You could, yeah, you could. I mean, you'd want to, yeah, I mean, you could do it, right? I mean, the key point is that you need to make f at least large enough so that, you know, it's, I mean, you could also do a more exact calculation here, but at least you want f to be larger than these degrees, otherwise you get nothing out of it. You could amplify, but I mean, the question you'd have to ask yourself is whether it's better moving to a larger field or whether it's better to amplify. And I mean, my guess is that it's going to be better to work in a larger field. Let me think a minute. I mean, it depends a little bit what you're trying to do, right? So like if you're given the field and you have to work in that field and you care about the sum over that field, there might not be anything you can do. In the application we're going to show in a minute, we actually care about an integer summation. And so there, all you need to do is make sure to work in a field large enough that you don't get overflow. And you can make it as large as you like other than that. So you may as well make the field larger. Okay. So just briefly, I want to recap the complexity of the protocol. So if we let capital T be the time to evaluate P, so what do we have? We have the number of rounds of the protocol is order of n, right? You have basically one back and forth interaction for each variable in your polynomial. The communication is order of the sum of di field elements. So why is that? Well, basically the communication is going to be dominated by the prover sending the polynomial to the verifier. And the polynomial in each step is going to have degree at most di. And so you need at most, you know, di plus 1 coefficients, or you can specify the evaluations, whatever. But you need order of di field elements to specify that polynomial in each round. And so you just sum them up, and that gives you the communication over the course of the protocol. The verifier time is basically just, you know, the cost to evaluate those di degree polynomials at each of the n iterations, plus one final evaluation of p at the end, which costs time t. And the prover time is going to be, basically, I mean, this is a little bit naive, but the prover time is going to essentially involve 2 to the n evaluations of the polynomial. So that's where you get the 2 to the n times t from. But also, if you do this thing where I said that you specify the polynomial pi by giving the evaluation of that polynomial at di plus 1 points, then essentially in each iteration you're actually doing that summation, that exponential summation, di plus 1 times. And so the prover time would actually be what's listed here. It doesn't actually matter too much because in the applications we're going to see in a minute, the di are going to be constant. So it doesn't really matter too much, but you can optimize things a little bit as well for those of you who like optimizing. The other thing I wanted to point out, and this is very important, is that the verifier actually, and this is a little bit surprising, the verifier does not need to know anything about P other than bounds on the degrees of the variables until the very end of the protocol. So nowhere in the protocol does the verifier use P itself at all until the final check. And this turns out to be very useful. We'll see actually in the GKR protocol how it's used critically. And in fact, and this will be important, I think, for some of the talks later on this week, V does not ever need to actually know P at all, as long as it has a way to evaluate P at a random point. You can imagine various settings. You can think, well, I don't want to, you know, take the thunder away from other people, but like you can imagine settings where, you know, the verifier doesn't actually have access to P written down. Maybe it's even too large to write down, but somehow it's able to obtain evaluations of P, and that's enough to run the protocol as well. It's kind of interesting feature of the protocol. Good. Let me give an application, and I'm going to do it a little bit quickly just for purposes of time, but really there's not much more than what we've already done. So what I want to show here is the power of interactive proofs and show how P, a prover can prove to a verifier about how many satisfying assignments a 3CNF formula has. Okay, so we know that 3CNF is an NP-complete problem. Deciding whether a formula is satisfiable is hard, but if I give you a satisfying assignment, you can check that it satisfies, and so it's easy to check. Here we're asking something much harder. We're asking the prover to convince a verifier that there are, you know, exactly 71 satisfying assignments of this formula and no more. Okay, and that's something that's not easy to check, and it's not believed to be an NP, in fact. So there's not believed to be any, you know, fast or polynomial time procedure that would allow somebody to verify such a claim. But nevertheless, we'll show how using an interactive protocol, the prover can convince the verifier of exactly how many assignments, satisfying assignments there are. And maybe you can already see where this is going, right? But the cool thing about this, if you haven't seen it before, is the idea of lifting Boolean formulas to polynomials. And this is called arithmetization. And we're going to arithmetize the formula by turning it into a polynomial in the following way. So we're going to take every Boolean variable xi, and we're going to, give it a we're going to call it a variable xi. Okay, great. We're going to take the complement of xi, right? If we have something where involving the complement of xi, we're going to turn that into the polynomial, right? 1 minus xi. So just again, so you can see where this is going, note that this has the property that if xi is equal to 0, so the complement is 1, well, 1 minus xi then evaluates to 1. And if xi is 1, so the complement is 0, then 1 minus xi evaluates to 0. We transform conjunctions by taking the product. So if we have two Boolean formula, phi1 and phi2, with respective arithmetizations, capital Phi1 and capital Phi2, then we can arithmetize their conjunction by multiplying the corresponding arithmetizations. And we can do disjunctions in a very similar way by just by this expression here, right? And the key point of this expression here is that when either of these evaluate to 1, this expression evaluates to 1. And if they both evaluate to 0, then the expression evaluates to 0. And so if we do this, then you get exactly this property. You get the property that if the Boolean formula evaluated at a particular assignment, b1 through bn, is equal to false, then the polynomial, capital Phi, that we constructed, evaluates to 0 in the field. And if we take the formula and evaluate it at Boolean values b1 through bn, and it evaluates to true, then the polynomial evaluates to 1 over the field. Right? No, these are actually not implied by each other, right? Because it could evaluate to some other random field element. Here, we're not in a field, but it could evaluate to who knows what. But it does indeed evaluate to 1 here. Is there a question on the back or no? Okay. Good. So now, right, I set things up for myself that the number of satisfying assignments of this Boolean formula is exactly the sum over the Boolean hypercube of this polynomial. Well, this polynomial, right, evaluated at all these points, b1 through bn. Maybe I should have called them x1 through xn, but whatever. That looks familiar. I hope it looks familiar. Right? So why does that look familiar? Well, it looks like exactly something the sum-check protocol can handle. So thinking about now a protocol for having the prover convince the verifier how many assignments there are, the first step in that protocol will be for both sides to independently arithmetize the formula, the deterministic procedure, so they can both do it and get the same answer.
We need to assume a big enough field now, right? For the
I'm not even in a field at this point. This is even over the integer. Yeah, I'm not even in a field yet. Yeah, this holds over the integers.
just thought when you wanted to say that the number of assignments is the same.
Yeah, that'll come in a minute, I guess. But for now, this is still true. Well, this is true, right? Because you get some integer, right? On the thing, positive integer. So now what we're going to do is, find some field that we want to work in. What we're going to do is we're going to pick. We're going to work in a prime field. It didn't have to be that way, I guess, but we need to do that. We need to be a little bit careful when we choose the prime, right? We want it to be large enough that the sum-check protocol will give us good soundness. That's fine, but we also want to make sure that we're not going to get any overflow, right? So if just thinking about it a minute, you have these 2 to the n assignments to the Boolean formula, and we're summing over them all. And so it could be that we have, 1,001 satisfying assignments. And if I worked mod 1,001, well, that would give me 0. And then the prover could cheat and claim that there are 0 satisfying assignments. So I want to make sure there's no overflow. So I need to pick the size of, or I need to pick Q at least as big as 2 to the n, because there might be 2 to the n assignments, and I want to make sure there's no overflow. Okay, good. And now I'm going to view this polynomial, right? That was so far only over the integers. I'm going to view it as a polynomial in that field, an n-variant polynomial in that field. Okay. And what I think is really cool here is that you've defined this polynomial phi based on its values in the Boolean hypercube. But now that you've defined this polynomial, right? Nothing stops you from evaluating it wherever you like. And you can evaluate it anywhere in this field. Okay, and that's really like, I don't know, a little bit mind-blowing, or it was to me when I saw it, right? It's really a cool feature. And this is like somehow the power of thinking mathematically about computational statements. So what now are the prover and verifier going to do? Well, now it's easy, right? We're pretty much done. All they're going to do is they're now going to run the sum check protocol with H0 being the claimed number of satisfying assignments, right? The prover knows, or it's claiming that it knows how many satisfying assignments there are. It tells the verifier, yeah, they're H0. They go ahead and run the protocol, okay? And then at the end, right, the prover will evaluate this polynomial just like before. It's going to be evaluating this polynomial that came from a Boolean expression. It's going to be evaluating it at random field points. But that's okay, right? Nothing says that we have to restrict ourselves to Boolean field elements, right? We have the power of working with the entire field. So you can indeed do that evaluation. You can do it efficiently. And that'll allow the verifier to check and see whether the prover was cheating or not. Okay, questions about that? Yeah.
Is the point of this to go towards a world where you can basically have computation be contained within polynomials, and then the outputs of functions are witnesses and stuff like that?
Yeah, I mean, that's where I'm going. I mean, at the time that this work came out, the goal was to prove things about complexity theory, right? And to just say, oh yeah, isn't this cool? This is the power of interactive proofs. Because actually, I mean, you know, like now we look back in retrospect and we know everything. So it's, you know, we're not surprised by anything anymore. But like at the time, there was a question about how powerful IP is. And, you know, immediately after it got introduced, people were sort of convinced it wasn't actually very powerful. There were some negative results even showing limits on what IP might be able to do in relativized worlds. And that made people think, oh, you know, it's not very powerful. But then, you know, the researchers came up with this protocol and they showed it's really quite powerful. And this was sort of a surprising and unexpected step. But the goal was to investigate the power of IP. Yeah, I'll come back to this point in a couple of slides. But
It's so unexpected because I mean the prover.
you expected?
I mean, the prover is still brute forcing essentially all the.
Yeah, but the verifier is running in basically linear time. I mean, plus the time to evaluate P and stuff. So the verifier is not doing anything, and yet it can learn from a prover the value. Yeah.
He said that the language was not in NP, or it's not known to be an NP.
Right.
And probably not an NP.
Well, nothing's provable around here, but
Yeah, but is it like?
it's let's see. I maybe someone else knows, but I think it's outside the polynomial hierarchy. So I think if you can do sharp P, maybe I take that back. I'm on video, so I don't want to say anything. But it's certainly not believed to be an NP. Yeah.
Okay, but IP is kind of the intuition that IP is a bigger class than.
Forget about look here.
Yeah. Okay.
P space. Okay, so you know, whenever you think about so actually yeah, P space we also don't know is different from NP. We know it's larger than P. We don't know whether it's different from NP. It's kind of obvious, and maybe you should prove it. But anyway, so you can extend the previous result to prove something even stronger, maximally strong actually. You can show you need one additional idea, which I could explain in 5 minutes, but I don't really even have 5 minutes. But maybe you should come to the Q&A session tomorrow if you like. You can show that P space is in IP. Like I said, P space is considered quite powerful. That is above the polynomial hierarchy, or at least contains the polynomial hierarchy. And it's tight in the sense that you can prove the reverse containment as well. This is not too difficult, that IP is contained in P space. So you know, IP is really quite powerful. And again, that did come as a surprise to people at the time. Yeah. Good. So let's then move on to the GKR protocol. We'll see how far we get. I don't know how much energy people have, but let's see how far we get. Good. So let me motivate the protocol. And I think this relates to your question a little bit. So let's say we have a prover who wants to convince a verifier about some computation done by a machine running in time t and space s. So what does this mean? It means that you and I, prover and verifier, agree on some Turing machine. We agree on some input. I ran the program and I claim that the output, is some value y, and I want to convince you of that. Now, maybe the verifier could just run the program itself. I didn't say anything about how large t and s are. Maybe it could run it itself. Fine. But maybe we want to also offload some of the work of the verifier and have it run faster than it would if it were doing everything on its own. So can we use these ideas from the sum check protocol to do that? Well, maybe we can, right? It depends a little bit on what TNS are, but you can reduce the computation of this machine, even if it's in P. You can reduce it to a P-space complete problem, and then you can use the result that P-space is in IP to prove something about that problem. We saw that in that protocol. Well, I didn't give you the P-space protocol, but it's similar to the sharp P protocol. The verifier is pretty efficient. We're just doing a bunch of polynomial evaluations. And so you could imagine that for some settings of T and S, the verifier is actually doing less work, and this will be a net win for the verifier. Now, the problem is from the prover's point of view. So the reduction would result in a formula on roughly S log T variables. And so the prover would require some huge amount of time, at least exponential for any reasonable values of S. So we said before we didn't care about the prover time, but that was before people started implementing these things, right? And then we do care about the prover time, and we want to get below exponential. And actually, even from a complexity theoretic point of view, it is really annoying that even if like the time is linear and the space is linear, we get an n to the n time verifier. We'd like to do better than that. And the problem fundamentally is that IP, the class IP, focuses entirely on keeping the verifier time polynomial without caring how expensive the prover gets. And this is, again, I think I said this earlier today, because it was motivated from the world of complexity theory. Certainly, those people don't implement stuff. And what we really want in practice and in cryptography is going to be doubly efficient proofs, by which I mean something where both the verifier and the prover run in polynomial time. And maybe we want even more than that. Maybe we want a prover to be linear time, but at least let's get polynomial time. So I'm going to show a protocol that doesn't quite get us all the way there, but it's a building block. We have to do a little bit more mathematical preliminaries. Now that's where the Galois theory can think. So let's let f be a function, arbitrary function on n Boolean variables. We'll say that a polynomial, a multivariate polynomial p, is an extension of f if the evaluation of p agrees with the evaluation of f for all Boolean values b. And we'll say that a multivariate polynomial p is multilinear if the degree of every variable is at most 1. I talked earlier about having low degree stuff. This is an example. We're going to get things we're going to focus on things that are multilinear. Everything has degree 1. I mean, total degree might be n, but each variable has degree only 1. And the lemma is that if we, one lemma is that if we have a polynomial, a multilinear polynomial that evaluates to 0 on the Boolean hypercube, then P must be identically 0, must be the 0 polynomial. Okay. This is actually some sort of an analog. This whole thing here is a little bit of an analog of like Lagrange interpolation, where if you have a polynomial, a univariate polynomial of bounded degree that evaluates it to 0 at too many points, then the polynomial must be the 0 polynomial. But there's something a little special going on about the fact that we're evaluating here over the hypercube. This doesn't work for arbitrary sets of points. And the proof is short, but I won't go through it again just for lack of time. You can look at it later. This is the entire proof. Good. So what I claim then is that every function f, no matter how complicated the function is, but it's a Boolean function. Well, it's a Boolean input. It can output a field element. It has a unique multilinear extension that I'll denote by f tilde. So in general, if I have a function, I'm going to denote its multilinear extension by f tilde. And the proof here is just to explicitly give such a polynomial. This is also very reminiscent of the flavor of Lagrange interpolation. So what we'll do is we'll first define for every setting of the Boolean values b, we're going to define a multilinear polynomial. It's given by this expression here, which you can stare at later if you like. But it's exactly analogous to Lagrange interpolation. And the main point of it is that when you evaluate it, this polynomial, when you evaluate it at x equals b, you get 1. And when you evaluate it at any other Boolean value, you get 0. So it's like an indicator polynomial. And the thing to note here is that this polynomial is multilinear, right? The variables here are the xi's. Right, the bi's are subscripted here. The variables of the polynomial are x1 through xn, and it's linear in each xi, so multilinear overall. And then we can define the multilinear extension of f to just be the sum over all settings of the Boolean variables b, f of b times this indicator polynomial chi b evaluated at the indeterminates x1 through xn. It's exactly like Lagrange interpolation, but now we're working with multivariate polynomials. Okay, so that gives us a multilinear extension. It's unique by the lemma I proved a little while ago that that if it's otherwise the difference would be the zero polynomial if two things existed that evaluate. Anyway, you get the idea. Good. Everybody okay with this? I'm going to skip this slide, I think. I didn't mean if you were okay with that slide. I meant. Everyone okay with that so far?
Blow up is not like big. The conversion from the
What do you mean by blow up?
the degree increase is not.
No, the degree doesn't increase, right? So this here is a multilinear polynomial, right? Why is it a multilinear polynomial? Because it's the sum of a bunch of multilinear polynomials. So the degree is not increasing, right? This is a multilinear polynomial.
Okay.
I mean, it's a product of many things, but they each are linear in each variable. Each variable has degree 1, at most 1.
And like real communication complexity, I'm a bit confused about like how.
Well, I haven't done anything yet.
Okay.
So yeah, I don't know. I haven't sent anything yet. So communication complexity 0. Yeah, I'm skipping this. Good. Okay, so now what I want to do is set up the GKR protocol, right? So the setting here is that we have a circuit. So that's going to be our computational model. The prover and verifier are going to agree on the circuit. Let's take the circuit to be a circuit of fan-in 2. So each gate in the circuit has just 2 input wires. And we're going to assume it's a layered circuit, by which I mean that the connections, right, the ingoing wires at any layer only come from the previous layer. It just simplifies the notation a little bit. It's not strictly essential, but it simplifies things. It's an arithmetic circuit over F, and there are n inputs and n outputs. So like I said, P and V agree on the circuit. They agree also on an input. And the prover wants to convince the verifier that when you evaluate the circuit at some input x, you get some claimed value y. Just some bookkeeping here. We're going to number the layers of the circuit from 0 to d, where 0 is going to be the output layer, and d is going to represent the input layer. Right, so, I mean, depending on how you count levels, it's a depth d or depth d minus 1. I don't know. I don't really care. But it's that's how we're going to number the levels. And we're going to also let the number of gates at level I, I'm going to denote that by capital SI, and just assume for simplicity it's a power of 2. So 2 to the little SI is equal to big SI. And now I'm going to define this function, WI, which is going to be the function specifying the values on the output wires at layer I for the given input X. Okay, so what does this mean exactly? This means, for example, when I plug in some Boolean value to WI, let's actually look at the easy case. We have the, let's say the input layer. So WD is supposed to specify the input. So WD is a function. It takes a Boolean input. That Boolean input is going to be, in this case, log n bits long, right? So capital SI corresponds to n. So it's going to take a Boolean input of size of length log n, interpret that as an integer in the range of 0 to n minus 1. That's going to correspond to one of the input positions, and it's going to specify what the value of the input at that position is. Okay? And at the output layer, right, W0, it's again going to be a Boolean function on log n Boolean variables. And when you give it a Boolean input, that specifies a particular index from 0 to n minus 1, and that's supposed to specify what the ith output of the function is. And W7 is supposed to correspond to the wires at layer 7, right? So the claim is that, and the verifier doesn't know this yet. I'm just defining some notation. So again, the Boolean variables are going to specify an index from 0 up to SI minus 1, capital SI minus 1. And that's supposed to tell you what the value on that wire is when you evaluate the circuit at the given input X. And what does V know? Right? P maybe knows everything because it can just evaluate the entire circuit. But V starts out only knowing WD, which is the function corresponding to the input layer, and a claimed value about W0. Right? The prover claims that the output has some particular value, so it's claiming something about the function W0. And I'm going to define further these indicator functions, add and mult, where add I is going to be what the so-called wiring predicate at layer I. So what does that mean? It's just an indicator function where you feed it the labels of 3 gates, one from level I and 2 from level I plus 1. And it returns 1 if and only if the corresponding gates from layer I plus 1 feed into the corresponding gate at level I. Right. So if and only if gates B and C feed into gate A, 0 otherwise. And I can define multi I didn't, yeah, right. And not only that, but it's an addition gate. And then multi is going to be defined similarly, except that saying it's a multiplication gate. Okay? And this only depends on the circuit, doesn't depend on the input, right? It's a function of the circuit only, and the verifier knows it as well. Whether it can compute it or not depends on some assumptions about the form of the circuit, but it's anyway only dependent on the circuit. And we're not going to ignore it, but we're going to assume that these are cheap to compute just for simplicity. And if it's a structured circuit, it generally is easy to compute. Okay, so now we're going to bring in the multilinear extensions. And the key fact that we're going to rely on is that you have this polynomial identity. Okay, what does this identity say? It says that the multilinear extension of Wi, which is supposed to tell you, right, you're supposed to evaluate it at a Boolean value and get a value for what value the wire takes at that position. If you evaluate it at, if you view it as a polynomial in A, it's equal to the summation over all gates B and C at layer I plus 1 of this expression here. Okay, so why is that the case? Let's just think about it. Well, forget about what I wrote here. You can look at that later. But the point is that if we take any particular gate A at level I, right, the value of that gate only depends on the value of the wires feeding into that gate from layer I plus 1. So as we take the summation here over all gates B and C at layer I plus 1, both add and mult, I should have subscripted those, but anyway, both add and mult are going to evaluate to 0, except at one single value. So for example, if A is an addition gate, then the only non-zero evaluation here will be when B and C are the 2 gates from level I plus 1 feeding into gate A at level I. And if it's a multiplication gate, the only non-zero value will be the corresponding one down here. Let's assume it's an addition gate. Well, that means that this indicator function is going to just pluck out a single value and everything else will be 0. What value is it going to pluck out? It's going to exactly pluck out the value of W tilde I plus 1 evaluated at B plus W tilde I plus 1 evaluated at C. So it's exactly doing the summation, right, of the values coming from wires B and C and coming out of gate A.
It's an extension, right? Or
On where?
Just a function. It's a.
Which one are you looking at?
It's Wi plus 1.
So it doesn't actually matter for this claim, but let's just take them as the extension. Yeah, the only thing that, because you're summing over B and C anyway, so it doesn't really matter. The only thing that's very important is that you need this to be multilinear in A. And then it'll match up the multilinearity over here. But we may as well make them multilinear in everything. Okay, so we've written the value of the value of the wire coming out of gate A in level I as some expression that's a summation over the values of all gates at level I plus 1. Now, only one of them is going to contribute to the sum, but we've still been able to write it as this big summation. And this should already make you think about the sum check protocol, right? So yeah, it looks like the sum check protocol might be useful. So let me just try to define some notation here, just because I run out of room on the slides. So I'm going to define this P tilde I plus 1 to just be this expression here inside the summation. So when we compute W tilde I evaluated at A, we're just summing this polynomial over all B and C. All right.
What does it mean, agree for all A in CO1?
I just mean that the expression on the left and the expression on the right agree for all Boolean A. So this is the core idea, and we can even maybe stop here and you'd get the main ideas out of this. So the main idea is the following. So we have this common input, the circuit C and the input X. We said already that the input X, which the verifier knows, defines this function WD. He is then going to send the claimed value Y, the claimed evaluation of the circuit. That defines some function W0 star. I put a star on it here because it might not be the correct value. It's just the value the prover sent. This is what we're trying to verify. And what the verifier is going to do, it's going to choose a random value R. This is exactly sum check. It's going to choose a random value R. Well, it's sum check plus. The verifier chooses a random value R. It's going to evaluate this polynomial. Sorry, it's going to take this W0 star, compute the multilinear extension of it, and evaluate that at the random point R. And that gives a value H0. And then they're going to run the sum check protocol with the claim being that if you sum over B and C, this value P1 tilde that I defined on the previous slide, and which is computable from W0 star and the add mult wiring predicates, the prover is, well, the verifier is asking the prover to show that the summation is indeed equal to H0. Okay? So like the way to think about this is that this summation on the right-hand side here, if you were just summing over Boolean B and C, that would just exactly give you the value. Well, sorry, if you were summing this over Boolean B and C, well, you are summing it over Boolean B and C. If R were a Boolean value, it's actually not just a single field element. It's a sequence of field elements. If it were a Boolean value, that would just be giving you the value of one of the output bits, one of the output field elements. But we're evaluating it exactly not on a Boolean, or not necessarily on a Boolean value, but on a random value. And that kind of gives us something about, well, it gives us a claim about the evaluation of this thing outside the Boolean hypercube. So let's see what the intuition is for why this should give us anything, right? And this is not the entire protocol, but let's see why this should give us anything. Well, let's let W0 represent the actual output, the correct output. So this just means, again, right, W0 is a function that takes a Boolean vector as input and returns the value of the output at the index corresponding to that Boolean value. If the value W0 star that the prover sent is not equal to W0, then they're different, then their multilinear extensions are going to be different. And so with overwhelming probability, if we set the parameters correctly, with overwhelming probability, these will not be equal. Right? Assuming that to be the case, assuming they're not equal, well, then that means that H0 is not the sum of P1 tilde over the Boolean hypercube. And so in that case, P is going to fail intuitively in the sum check protocol. Okay, so it's using the same ideas of evaluating things at random points, the same ideas that we saw in the sum check protocol. Now the problem here, okay, I think, well, we can decide when we end, I guess, but let me define some natural stopping point, and then I'll let you know, and you can tell me what you want to do. The problem with this, the way I wrote it here, well, there's no problem with it except for one thing, is that what do we do in the sum check protocol? Well, at the end of the sum check protocol, the verifier has to evaluate this polynomial at a random, a random sequence of points, or a random point, essentially, right? Remember, that's how the sum check protocol works. You don't do anything with the polynomial till the end. Question?
These are not the same random variables that we choose in step 2.
What's not
in
the
that
same?
sense. No,
I mean,
the
this step here is independent of this step here.
Oh, okay,
That's what I'm
okay,
asking.
yeah.
Yeah, here we chose a random R, then we apply the sum check protocol here.
Okay.
This R is the same.
That's the same from step 2, or
Yeah, that's the same from step 2. Yeah, yeah. And then if you just think about it, right, the sum check protocol is then going to peel off, each thing of B and C one at a time and replace them with random values. Yeah, that here I'm calling B1, C1. So at the end of the protocol, V has to evaluate P1 tilde. Now, I don't know if you can remember at this point. I'm having trouble remembering. What does P1 tilde depend on? P1 tilde depends on W1 tilde. What was W1 tilde? The value of the output wire, or the value of the wires at the previous level of the circuit. The verifier doesn't know the value of the wires at that level of the circuit. Well, let's see. I mean, the prover could send W1 to the verifier, but if it does that, it's going to just end up sending the values of the wires at every layer of the circuit. And you're not going to gain anything versus evaluating the circuit on the verifier is not gaining anything compared to just evaluating it on its own. So instead, we're going to do something a little bit funny. What we're going to do is we're just going to have P, tell the verifier the values of W1 tilde evaluated at the right point at B1 and evaluated at C1. And that's a little weird, right? The prover, we're supposed to evaluate it to catch a cheating prover, but now the prover is telling us what the values of that polynomial are. So how are we going to make sure that the prover doesn't cheat in that step? Well, we're going to have to recursively verify what the prover tells us about these values, right? The prover is now making a claim about the values at layer 1 of the circuit, and we're going to reduce that to a claim about the values at layer 2 of the circuit, and keep going up until we reach the input layer. So I think I will skip this slide, unfortunately. I'll just say that recursion, there's a little non-trivial step involved. We can go over it. I'm happy to stay if people want to stay and have questions, but there's probably some drinks of some sort outside. It becomes easier after a beer, I think. It becomes you really gain mental clarity on the protocol, especially after 2. Wow, yeah, you believe anything. So let's just see what the protocol is going to look like, right? So, and there's some stuff here that was on the slides that I skipped, but the basic idea is that the prover sends a value y that defines this function w0. The verifier chooses a random point, evaluates the polynomial at that random value, gets a value h0 that it's going to then run the sum check protocol on. We get to the end of the sum check protocol, and then V needs these values, w tilde, right, in the first iteration it'll be 1, in the ith iteration it's I plus 1. And V needs those values, okay? Where does it get them from? It gets them from the prover. The prover tells the verifier what values to use. And then the prover, presumably they're going to make the verifier pass the check, unless the prover is an idiot, right? So then what happens is that will reduce to a claim about what's going on 1 layer up in the circuit. And we keep proceeding in that way, reducing a claim about level I to a claim about level I plus 1, until they get to the input layer of the circuit. Now, when you're at the input layer of the circuit, at that point, the verifier is doing really well because the verifier does have the input. It knows the input, and it can evaluate the multilinear extension of the input. And it can then do this final check on its own without relying on the prover to see whether the prover was cheating or not. This is the multilinear extension of the input, evaluating it at a random point that was chosen during the course of the protocol, checking that this value HD is equal to that evaluation. And if not, it knows the prover was cheating. And if it does work out, then with overwhelming probability, the prover's claim was correct. So I think I will stop there. Let me see if I have anything else interesting to say. Yeah, I mean, a little bit about the complexity. Yeah, let me just say one word about the complexity here. We can go through it a little bit quickly. I mean, the main point here, the main thing we're interested here is the verifier time and what we can say about the verifier time. And the main takeaway is that if you unpack the protocol, so first of all, there are D iterations because we're going layer by layer in the circuit. And so this GKR protocol in general is really only going to give you something good for the verifier if it's a shallow circuit, if it's a low depth circuit. But if you have a circuit with n gates, but they're all in a line, and so you have n levels, you're not really gaining anything. So, you need to assume that the depth D is relatively low. And other than that, the amount of work that the verifier is doing at each iteration is only going to be dependent on the number of Boolean values you need to specify the gates in that level, right? Because if you think about the sum check protocol, right, you're going 1 by 1 through the variables that are being summed over. And we set things so that the number of variables you're working with is log of the number of wires in that gate. So you're never doing more than log in the total size of the circuit at any level. And so the overall work of the verifier is D times the log of the number of gates in the circuit. So if you have a very wide circuit, but very shallow, the D is small, but the total number of gates can be large, then you get a huge speed up here for the verifier because the verifier is able to evaluate a claim about the output of the circuit using only D log C work other than reading the input and output. And this does make an assumption that evaluating add and mult is easy. So, maybe you can cook up a circuit for where that's not the case. But as I said earlier, I think for circuits that people care about in practice, that typically is the case. And so it's not really an issue in the overall protocol. So I think I can stop there. I have, things to say, but I don't want to keep anybody. Okay, I'll say one more thing. I just want to say the last thing to set people up for maybe later in the week. So this, what we really want, remember, is we want some doubly efficient protocols. We want something where the verifier, yes, is doing better than evaluating things on its own, but also it's feasible for the prover to like do the work of convincing the verifier. And the GKR protocol gives us a big step in that direction, right? It doesn't get us fully there because we're only dealing with low depth circuits, but it's a big step in that direction. And the ideas in the protocol and the ideas behind the sum check protocol are very useful in building up many proofs that do get us further there. And so I think you'll see some of that coming up later on in the talks this week. So I'll stop for that for now.